So we're in the last section of this chapter on sequences of series, infinite series, and this one may be the most practical as far as maybe you could see the use for it easier than the other sections that we've done. So this is covering Taylor series. And so I guess the question, and we kind of asked this in the last video towards the end on the power series, can we replace a complicated function with a polynomial that behaves almost the same near a particular point? Um, so we're going to start with an idea that you would have seen in Calculus 1. So one topic that's covered in all Calculus 1 classes is linearization. So when you have some curve, um, what is going on near some point. So you pretend like the function is linear around that point. So we're going to kind of do the same thing, but we're going to get a little bit more detailed as far as instead of assuming it's linear, we're going to assume that whatever complicated function we have, and this is not a complicated function, but we'll just say exponential. Can we get a polynomial that looks like this around a particular point on that function? That's the idea. So if we start with a tangent line, so this is where we would have gone in Calculus 1. So start with a tangent line. So this picture here. What was that formula? So f of x was approximately equal to f of a. So this is the point x equals a, plus f prime of a times x minus a. So we had that formula in Calculus 1. Spent a whole section probably on linearization and that kind of thing. Now, we could also add a quadratic term. So if we wanted to, instead of making it linear, we can make it quadratic. And so this would look more like f of x is approximately equal to, now we're going to call this c sub 0. And then we're going to add c sub 1 x minus a. And then we're going to add c sub 2 x minus a squared. Now, we'll figure out what the c terms are, the c coefficients are. So now suppose we have this power series. So this is an infinite polynomial or a power series. We looked at these last time. So let's figure out what these coefficients are, the C0, C1, C2, and so on. So if we plug in A into P, so P of A, all these terms will go away. So x minus a, if we plug in a, that's 0. X minus a squared, all the x minus a's are going to be 0 if we plug in a for x. So P of a is going to be c sub 0. Now we know that we need that to equal f of a, so this will just be f of a. So c sub 0 is just f of a. Now let's take the derivative of p. So with respect to x, so the c0 goes away. This will just become c1. Now this will become 2c2 x minus a. This would become 3c3 x minus a, and so on. Now when we plug in a into the derivative, all these terms are going to go away, and p prime of a is going to be c1. Which, as we can see, this would be f prime of a. So c1 is going to be f prime of a. Now, you might be thinking that c2 will be f double prime of a, c3 will be f triple prime of a, but that's not the case. So let's take the derivative again. c1 goes away when we take the derivative. This term becomes 2c2. This should be a squared here. Forgot about the square. Now, this term would be 6c3 times x minus a. If we want to go to the next one, so here we'd have 4 c4 x minus a to the third. So now that would become 12 c4 x minus a squared, and so on. So now when we find p prime of a, all these terms go away. That will be 2c2 and we need that to equal f double prime of a. So this tells us that C2 is f double prime of a over 2. Now, the way it works out, and you could keep going, you could go to the third derivative if you wanted to. I won't work that out. But if you keep going, C3 will be f triple prime of a over 6, which is 3 factorial. C4 would be f to fourth derivative evaluated at a, 4 factorial. And if we want to get the nth term, Cn, that would be the nth prime evaluated at a over n factorial. So what we end up with, if we want to get this formula and replace the c coefficients with their derivative form, however that might look, we would end up with p of x equals f of a plus f prime of a, x minus a, plus f double prime of a over 2, x minus a squared, plus f triple prime of a over 3 factorial. And this is 2 factorial, but 2 factorial is just 2. F triple prime of a over 3 factorial, x minus a cubed, and on and on. Now, one of the things I want you to, or that you're going to need to get good at, that you may not have done a whole lot in the past, is when you look at this series, and maybe we did this in the last video a little bit, when you look at this series, can you write this in summation notation? So we have the sum from n equals 0. So notice the derivative. So we have the 0 term here, the first term, the second term, the third term, so on. So notice the derivative matches the number term that you're on. So we know we're going to have the nth derivative of a. So kind of we're basically writing the nth term here. Over, now 0 factorial is 1, 1 factorial is 1, 2 factorial, 3 factorial, 4 factorial. So we have n factorial here. And then we have x minus a to the 0 power, first power, second power, third power. So that also matches whatever term we're looking at. So if we're on the nth term, that would be to the nth. So here is our approximation for f of x. So f of x can be any function that can be infinitely differentiated. And if that's the case, then we can write this infinite sum so that at around this point A, this series will approximate f of a. All right, so let's look at an example. So the first example is e to the x. And we're just going to let x equal 0 for simplicity. So what happens when x equals 0? So we know that all the derivatives of e to the x are just e to the x. We don't need to write out f prime, f double prime, and so on. They're all going to be e to the x. So this is for all n. And so if that's the case, we also will know that f n, the nth derivative evaluated at 0, will be e to the 0, which is just 1 for all n. So now let's plug in this formula. So e to the x is going to be, so we have, we'll write the formula out again. F of a plus f prime of a plus f prime of a times x plus f prime of a x squared. Now it's x squared because it's x minus 0. So x is, the a is 0. I guess we should say a is 0. A is 0. Over 2 factorial plus f, that should be double prime, triple prime of a over 3 factorial x cubed, on and on and on. Okay, so now let's plug in what we have. So we know f of a is going to be, or f of 0, these are all zeros. F of 0 is going to be 1. F prime of 0 is 1 times x. So all these are going to be 1. All these derivatives are going to be 1. So now we get x squared over 2 factorial, x cubed over 3 factorial. We want to keep going, x to the 4th, 4 factorial, and so on. So now can we write this as a sum? So sum from 0 to infinity. And just imagine, so we have the 0 term, the first term, the second term, the third term, the fourth term. So just say the third term. We have 3's all over. So we could write x to the n over n factorial. And so this is going to be our Taylor series for e to the x. Okay. So that's kind of the idea of what we're doing. We're using this formula that we had up here. We're going to find derivatives. We're going to write out a few terms and then figure out the pattern. So that's essentially what we're doing. Once we write out these terms, we're going to figure out the pattern. So let's try sine of x. And again, we'll do this at a equals 0. So we have f of x is sine of x. F prime of x is cosine of x. F double prime is negative sine of x. F triple prime is negative cosine of x. And then, of course, we're going to repeat, cycle back through. All right, so now let's evaluate these at 0. So f of 0 would be 0. F prime of 0 would be 1. F double prime of 0 would be 0. And f triple prime of 0 would be negative 1. So you can see the pattern is going to be 0, 1, 0, negative 1, 0, 1, 0, negative 1. So if you just keep going, that's what the pattern is going to be. Okay. So now, sine of x is going to be f of 0 plus f prime of 0 times x plus f double prime of 0 x squared over 2 factorial plus f triple prime of 0 x cubed over 3 factorial, on and on and on. So now let's fill in what these are. F of 0 is 0. F prime of 0 is 1 times x is x. F double prime of 0 is 0. F triple prime is negative 1 x cubed over 3 factorial. And so on. All right, so now let's get rid of the 0 terms. So we have x minus x cubed over 3 factorial. And you can imagine, if you need to, you can write it out, but you can probably imagine this will be x, the next term that we have, the non-zero term, will be x to the 5th over 5 factorial. And then the next term will be minus x to the 7th over 7 factorial, and on and on and on. So write out as many terms as you need to start to see the pattern, because there will always be a pattern. And now we have the sum from 0 to infinity. So what do we have? So the first, or the 0 term, the first term, the second term, the third term. So we have x. If we're on the first term, we go up by 2. If we're on the second term, we go up by 3. So we could actually do 2n plus 1. And that would give us, so if n is 0, that gives us x to the first. If n is 1, that gives us x to the third. If n is 2, that gives us x to the 5th. So that's good. And then the exponent matches whatever the factorial is. So we're going to need 2n plus 1 factorial. Now, the one thing we didn't also account for is the alternating sign. So we're going to have negative 1 to the n. So it's either going to be negative 1 to the n or negative 1 to the n plus 1. So if we do negative 1 to the n, the first term will be negative 1 to 0, which is 1. So that's positive. The second term will be negative 1 to the first, which is negative 1. That's negative. So we have our signs correct. And obviously, most of the time we'll write that, but I forgot to write that in the beginning. But order doesn't matter since we're multiplying anyway. So there is our Taylor series for sine of x. Okay, so now you notice we've evaluated these at 0 so far. You could pick any number for a, as long as it's in the domain of the function. But a equals 0 comes up a lot, and so this is actually called, don't need the G there, it's a Maclaurin series. So a Maclaurin series is simply a Taylor series centered at 0. And so this formula is just f of x is going to be the sum from 0 to infinity. F, the nth derivative, evaluated at 0 over n factorial x to the n. And so this is just the Taylor series, but we're plugging in 0 for a. And so it's not x minus a, it's just x. All right, so let's look at cosine. And again, you need to know the formula, but the other big skill that you need to be good at is recognizing these patterns and be able to write the pattern into an infinite sum like this. So let's write out our derivatives. First derivative is negative sine, second derivative is negative cosine, third derivative will be sine, and then we're back up to cosine. So f of 0 is going to be 1, f prime of 0 is going to be 0, f double prime of 0 will be negative 1, and f triple prime of 0 will be 0, and it'll just repeat. So we have 1, 0, negative 1, 0, and so on. Okay, so we're just letting a equal 0. We're looking at the Maclaurin series. So let's write out our terms. So we have cosine of x equals 1. So f of 0. The next term will be 0. But maybe you want to write it just so we keep everything straight. And then we have minus x squared over 2 factorial. And then we have a 0x cubed. And then we have plus x to the 4th over 4 cubed, plus 0x to the 5th, minus, and so on. And so we get rid of our 0 terms. We have 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial. And that would be a minus, but on and on and on. Okay, so now what do we have when we write this as an infinite sum? So n equals 0 to infinity. And so we know we're going to have a negative 1 to the n, or n plus 1. So the first term is positive, so it's going to be negative 1 to the n. Now we have the 0 term, the first term, the second term, the third term, and so on. So notice that the first term has an exponent of 2. The second term has an exponent of 4. The third term would have an exponent of 6. So our x is going to be raised to the 2n. So the exponent is double whatever the term is, whatever number term we're on. And then also we have 2 factorial, 4 factorial. So the exponent matches the factorial. So whatever that is, we also have down here. And then it's going to be 2n factorial. So this is our Maclaurin series for cosine of x. Now, I did put a table of the common ones that you see in the page on Canvas. So you can look at those. It's possible you can memorize those, I guess. I don't know that I'd recommend it, but it might actually be good practice to look at those and see if you can derive them yourself, because they're so similar. Notice this one is very similar to the cosine one, or the sine. If we go back to sine, the sine series was, I have it, where did it go? Well, let's scroll back up here. See, I can't remember off the top of my head either. Negative 1 to the n, x to the 2n plus 1. So negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Okay. All right, so let's stop there, and then we will continue with some more examples in the next video.